So now let's solve the 2014 question 4, thermodynamics. Okay, so he gives you the graph in the question. I just added this arrows, but he tells you in the question that he starts from A, goes to B, and then C, and then D. Okay, so this is the thing. So he starts with pressure 0 and volume 0, and then he goes to B in a constant pressure, right? But the volume increases from A to B. The pressure is constant and the volume increases. Okay, from B to C you have constant volume. You don't change the volume from B to C, but you will increase the pressure. From B to C you increase the pressure and the volume is constant. From A to B you increase the volume and the pressure is constant. Okay, in C to D you will maintain the pressure constant, but you will decrease the volume. And from D to A you will maintain the volume constant. This is not minus, okay? Just for me to say that it's staying still, it doesn't go up or down. Okay, I hope it's not making any trouble for you. And the pressure goes down. Okay, so just let me take that off. So why is this important? Well, because if you know what is changing, you know, like, it all goes down eventually to this one. Okay, the heat is equal to the internal energy plus the work. But you need to know which one is changing. Like, for example, from B to C you don't have change in the volume, right? Remember, from B to C. So if you don't change the volume, then the work is 0. Okay, so this is, so let's start solving. Okay, take the question, try solving by yourself, and I'm going to start solving it now. So this is a long question. The first part of the question wants you to relate the temperature in point C with the temperature in point A. It wants a relation with this two, remembering that the temperature in point C is this one and the temperature in point A is this one. If you have seen this, like, this is the temperature curves. Okay, don't bother if you didn't see them yet, just bear with. I won't talk about them right now. Okay, so look, the temperature C and the temperature A. Well, what do we know? We know that pressure in point A versus volume in point A divided temperature in point A is equal to NR, right? Remember that PV is equal to nRT. You need to remember this. The temperature went to the other side. Okay, so pressure in C, volume in C divided by the temperature C is equal to NR. So the material is constant. Okay, so pressure in A, volume in A divided by the temperature in A is equal to pressure in C, volume in C, temperature in C. You need to always remember this for thermodynamics. And now that we know that the material did not change, we have, like, he doesn't say that we lose or it goes to the out anything. So now we just need to find what is PA, VA, PC, and VC. So he gave us this in the graph. So PC is equal to 4P0. Okay, so PC is 4P0, and volume in C is 3V0, volume in the point C. So 3V0 divided by temperature in C. The pressure in A is P0, and the volume in A is V0 divided by temperature in A. So we have V0, P0, P0, V0. So we know that the temperature in C, this goes there and this goes there. Here we have equality, right? So the temperature in C, 4 versus 3 is 12. Temperature in point A, okay, which give us G. He asked what multiple of temperature at C is that at A? Well, it is 12. You multiply the temperature of A versus 12 to get the temperature of C. So the answer is G. Okay, now let's go to question 2. He wants the work. Find the work done in the process from A to B. Now so look, now this is another thing that you need to always remember. The work done when the pressure is constant is P, the variation of the volume. Okay, now if the pressure was not constant, it would be another expression. You will need integral. Okay, but I didn't see the max cover that yet. This is the thing that, like, this is the second question that I'm solving that uses this one. Okay, so it is important for you to remember the work done is the pressure versus the variation of the volume, and we want the work done where? From A to B, right? So this is wonderful for us porque from A to B the pressure is constant, it is P0, and the variation of the volume is, we go from V0 to 3V0, so 2V0, right? 3V0 minus V0, 2V0, right? The variation of the volume is the final volume minus the initial volume. So the work from A to B is equal to 2P0 V0. And where can we find this? Well, let me look over here. F, right? Yeah, in the alternative F. 2P0 F0. Nice. Now to solve the question 3, like, we will end up solving the question 4 with it. Okay, but you don't really need to, like, so look, we will solve the question 3 by analyzing the graph first and come to a logical conclusion. Okay, but after it we will do the math, where when we're solving question 4 we can do the math, and then we will prove it again that the answer for question 3. Okay, so look, in question 3 he wants you to choose the process in which the thermal heat the gas receives from outside is at maximum among 4 processes. So he basically wants that the maximum heat, right? Remember? So he wants this, the maximum, this one, right? So look, now if you studied cycles in thermodynamics, look, what is the internal energy? So the internal energy for this monoatomic gas, 3 divided by 2 nRT, right? So look, it only depends on the temperature. The more the temperature grows, the more you are receiving heat, because the more you are growing your internal energy, I guess you could say. So look, in this process A to B, well, you are gaining work and internal energy because the temperature is growing. So it might not be so obvious by just analyzing, so we're going to solve it by math and physics, okay? But the thing is that from B to C, you're not doing any work, and all the energy is growing and the temperature is going up. So look, what we are going to need to find right now is how much energy this key for each of the process. So we will need to find the internal energy. We did find the work from A to B. We will need to find the internal energy from A to B, and then from B to C, and then that will be good enough. Why? Because from C to D he is losing energy. The energy will be negative. Why is that? How can I know that? Because look, number one, the temperature is going down. How do I know that? Well, you have the same pressure, but you're losing volume. If you're losing volume, so you will eventually be losing temperature together. Look, so PV divided by T must be PV2 divided by T2. If the pressure is constant, so V1 divided by T1 must be V2 divided by T2. If the volume decreased, volume 2 was bigger than volume 1, then that temperature must decrease so that we can maintain this equality, okay? So we're going to be losing heat over here, and over here we'll be losing really much, really heat. So if you didn't understand this well, we're going to calculate all this right now, okay? So with physics and maths, so I hope it can be helpful. So and you can always do this, okay? These curves over here in the graph of pressure per volume, these curves, it helps you find the temperature. If the curve is far from the center, means that the temperature is bigger, okay? So this has the highest temperature, and then we have this one over here, P and D, they have the same temperature. I think they have the same temperature, right? We can calculate it. We will calculate. And this one has the lowest temperature, okay? You can always, if you don't believe like what I'm saying, you can check it out. PV equal to nRT, and then check it for each of these occasions, okay? So now let's calculate. What we're going to calculate is the heat for each of these processes, okay? How are we going to calculate it? By finding the work they did in the process plus the internal energy in each one of them. If you want to do it by yourself, it will be much faster for you, okay? So I'm going to start doing it now. So the heat from A to B the heat he received will be the internal energy plus the work from A to B. Remember the work we just found from A to B, we found it for eating 2, right? So all we need to find now is from A to B, the internal energy plus the work is 2P0 V0. So how can we find the internal energy? Well, the internal energy 3 divided by 2 nRT, right? So we're going to, so you'll need to find the, this is a variation of temperature, okay? So we want to find the internal energy from A to B, right? So 3 divided by 2 nR, and then we will have that final temperature, the temperature in B minus the temperature in A. You can even do, like, if you want, 3 divided by 2 is equal versus, now this part over here is actually P versus the volume in B minus volume in A, right? Because PV is equal to nRT, so I'm taking the part nRT and putting PV, and this PV we did calculate, it is 2P0 V0, okay? So, but if you want to solve this one, there's no problem, okay? Temperature in B minus temperature in A. How are you going to solve it? Well, you will need to find the temperature in B and the temperature in A. How can you find them? Well, look at the graph. I'm going to do it over here, okay? So you know that the pressure in A, volume in A, divided by the temperature in A, I will actually do it different, okay? I will do it over here. We know that, look, we know that the pressure in A versus the volume in A is equal to nR versus the temperature in A, right? And the pressure in B, volume in B is equal to nR, temperature in B. So this one is going to be 2 and this one is going to be 1. Now I want you to take the equation 2 minus the equation 1, okay? So what I'm telling you, basically, it's PB VB is equal to nR TB minus PA VA is equal to nR TA, okay? So if you do this minus, what are you going to find? Now you're going to find PB VB minus PA VA is equal to nR TB minus TA, right? And what is the pressure in the point B? The pressure in point B is P0, and the volume in point B is 3V, right? Just look at the graph in the question. And the pressure in point A is P, and the volume is V, is equal to N R TB minus TA. So 3 VP minus PV is 2 PV equal to nR TB minus TA. And this is what we just said, right, over here. Right. Over here we said that we can exchange this part nR TB minus TA, because nRT is equal to PV, so we could use that it is PV, and we did calculate PV. So we did it with two different sides, okay? So remember what we're so going back, the heat in point A, B over here is equal to the internal energy, which we just found. It was 3 divided by 2 versus 2 PV plus the work. Well, the work was 2 PV, right? So this 2 divided by this 2, and the work, the heat from A to B is equal to 3 plus 2, 5 PV. Okay, and now we're going to need to do the same thing for the process from B to C, but now it's going to be easier. Why is that? Well, because we will only have internal energy. Why we don't have work now? Remember, because here we don't have variation of volume. Okay, so the work done is equal to 0. All the heats put in here is going to increase your internal energy. Okay, so from B to C the work is 0. Okay, so from B to C, all we're going to have is 3 divided by 2 nR, the variation of the temperature, Tc minus Tb. Now remember, we can we can't now use PV over here, okay, because the pressure is not constant. Okay, well, like, you can use it but different. You can't like say the pressure is constant and do the variation of the volume. You can do it like the volume is constant and do the variation of pressure. Like, I don't know if this is physics is correct, but like it does give you the same result. Okay, but like I'm going to do it with the two forms. Okay, so 3 divided by 2. Now nR versus this one is equal to P variation, volume variation of the pressure. Why? Remember again, because now the volume is constant, so the volume from B to C is going to stay constant, and it is 3V0. Okay, over here 3V0, the in point B. Okay, and what about the pressure? Well, the pressure goes from B, the pressure in B, it is P0 in point B, and then it goes to 4P0 in point C. So the variation of the pressure, remember, the variation of the pressure is pressure final minus pressure initial. So 4P0 minus 1P0, 3P0. Okay, so 3 versus 3 versus 3, 27 divided by 2 V0 P0. Now remember, this is the, I'm going to do it by the other way, okay, just to make sure, but just remember, this one is this is the heat in from B to C. Remember, from A to B we found it was 5P0 V0, right? So it was 5P0 V0. Now look, the heat from B to C, it is much higher. It is much higher. It is more than twice. Okay, so from B to C it is higher than A to B. So B to C received more thermal heat. Okay, now you might argue like, okay, so B to C is received more than from A to B. Now, do we need to find from C to D and from D to A? Well, you can find it in the Google Drive paper. I did calculate them, okay, but we won't do it in video because it is already too long. But look, from C to D, you remember what I said in the beginning of the video, you are starting to lose heat, okay, and from D to A you are losing heat, so you are receiving It is a cycle, okay? And this is the biggest part of it. So just to end it, like, if you want, I won't do it, but if you want, just remember, like, pressure in point B, volume in point B is equal to nR, temperature in point B, and just wait a minute, pressure in point C, volume in point C is equal to nR, temperature in point C. Subtract this one from this one, okay? So you have that PC VC minus PB VB is equal to nR TC minus TB, okay? And then you will find this part over here by putting the values of PC and VC, and you can find the same thing, okay? And I think so. I don't know if this oh, okay. So the last one, now he want the net thermal heat. Now I think when he said the net thermal heat, he is asking the total work, okay? So I think, I'm not sure, I didn't know this word before this question, okay? The net thermal heat. So in this graph, the work done is given by the area of your graph, okay? Pressure by volume. Why? Because because remember that the work is pressure versus volume, okay? But if you don't have none of them constant, you will need to do the integral. You need to integrate, but as this is only, you can find the area of this, you don't need to integrate, you just find it, okay? 2v0 over here, 3p0, so multiply, so you will have that the work is equal to 2v0 versus 3p0, 6p0 v0.